Lesson 8-2, Properties of Logarithms. A logarithmic equation contains one or more logarithms. The first property we want to look at is the property of equality for logarithmic equations. It says if b is a positive number other than 1, then log base b of x equals log base b of y if and only if x equals y. So if the bases are the same for logarithms, then your x is going to equal your y. So the example, log base 3 of x equals log base 3 of 7. So x would have to equal 7. So just like we have exponentials, when the bases were the same, the exponents equal. The same is true for logarithms. And this would be the same thing for inequalities instead of equations. So inequalities and equations would work the same way. So for here, we need to solve log base 4 of x equaling 5 halves. To solve this one, we're going to start with base 4 of 5 halves equals x. So we'll have 4 to the 5 halves power will equal x. The square root of 4 is 2, and then 2 to the 5th power will give us x. That means x would equal 32. Next, we have base 81 of 34 equals x. So 81 to the 3/4, not 34, 3/4 equals x. The fourth root of 81 is 3. And then 3 cubed is going to equal x. X would equal 27. Next, solve these using properties of equality. So again, we have our bases of our logarithms equal. That means the rest are going to be equal. So I have 2x squared minus 6 equals 4x. And now I'm going to solve this quadratic. And in doing that, I'm going to make everything equal to 0. So I'm going to subtract 4x on both sides. Now I have 2x squared minus 4x minus 6 equaling 0. Here I can factor out the greatest common factor. That would be a 2, so that leaves me with x squared minus 2x minus 3 equaling 0. So if I factor this completely, I would have minus 3 and a plus 2, or plus 1, I mean, because negative 3 times 1 is negative 3, and negative 3 plus 1 is negative 2. If I make each factor equal to 0, this equal to 0, this equal to 0, and this equal to 0, 2 can never equal 0, so I don't worry about that. X minus 3 equals 0. X would have to be a positive 3. And over here, x would have to be a negative 1. Now, if I need to check to make sure that both answers work in my original equation. Now, I cannot find a logarithm of a negative number. And since I put a negative 1 in for x here, I would have a log base 5 of a negative 4. That will not work for that. So negative 1 is not a solution. That is actually extraneous. So my only solution would be x equaling 3. Now, if this was a negative 4, then I could have a negative 1 there. But because my original equation only has a positive, I can't have a negative x value. Next one, solve this one. Bases are the same. So now I have 8x equaling x squared minus 33. Make this equal to 0. I'm going to subtract 8x on both sides. And now I have 0 equaling x squared minus 8x minus 33. Then factor. So I got to think, what do I multiply to get 33, but add them together gives me 8. So this would be minus 11 and a plus 3. Because a negative 11 plus 3 is negative 8. I make them all equal to 0. X could equal positive 11, and x could also equal a negative 3. If I plug those back in, this side, if I put a negative 3 in here, we'll make it a negative logarithm, and I can't do that. Can't find that one, so my only solution would be 11. Next, solve this one. Bases are the same, so everything else has to equal. So negative 5x equals a negative 2x squared plus 3. Here I'm going to bring everything to the left-hand side. So I'm going to add 2x squared minus 3. Now I have 2x squared minus 5x minus 3 equals 0. Okay, I'm going to factor this, so this will give us a negative 6x squared. Now I think, what do I multiply to get negative 6? But m together gives me negative 5. This would be a negative, or a positive 2x and a negative 3x. Actually, no, that'll be a negative, see, a positive 1x and a negative 6x. Then bring down the sides. Factor, so here I would have an x plus 2. And on this side, I would have, this is x squared. So I can factor out a x, and that will leave me with x plus 1. Over here, I can factor out a negative 2. This would be a 2x plus 1. I can factor out a negative 3. That leaves me with 2x plus 1. So my two binomials would be 2x plus 1 and x minus 3. Make each of them equal to 0. This one would be x equaling a negative 1/2. This would be x equaling a positive 3. Now if I plug that back in, you'll notice this side has a negative number. So that means my x has to be negative. And the only one that has a negative x would be x equaling negative 1/2. The reason why this has to be a negative is because a negative times a negative gives you a positive, and I can find a positive value there. This one, could I get if I put a negative 1/2 in here and square it, that's going to give me 1/4. 1/4 of negative 2, so negative 2 times positive 1/4 is going to give us a negative 1/2. And negative 1/2 plus 3 is still going to give me a positive answer. That would give me 2.5 or 2.5. That's why x would be negative 1/2. The next property with logarithms, because logarithms are exponents, the properties of logarithms can be derived from properties of exponents. For example, the product property of logarithms can be derived from the product of powers property of exponents. The product property of logarithms then would be the logarithm of a product is a sum of the logarithms of its factors. When you think of exponents, when you multiply like bases, you add the exponents. So the logarithms of a product is the sum of its logarithms of its factors. So for all positive numbers, b, m, and n, where b cannot equal 1, the logarithm of b of mn is the same as log base b of m plus log base b of n. So we're just expanding the logarithm here. The log base 5 of 8 times 4, or if it was log base 5 of 32, you would just say it as log base 5 of 8 plus log base 5 of 4. You can use the product property of logarithms to approximate logarithmic expressions. So the logarithm of a quotient is the difference of the logarithms of the numerator and the denominator. So that's for all positive numbers, b, m, and n, where b cannot equal 1. If I have a division, log base b of m divided by n, you would also have subtraction here. So when you're expanding it, it's subtraction. So just like we have with dividing like bases, you would subtract the exponents. You do the same thing with logarithms. So log base 8 of 2/3 would be log base 8 of 2 minus log base 2 of 3, or log base 8 of 3. And then we have the power property of logarithms. says a logarithm of a power is the product of the logarithm and the exponent. So for here with a logarithm, if you have a logarithm b of m to the n power, you can write that with the n going in the front as a multiplication, and you'd have n log base b of m. Now, the power property of exponents means when you multiply like base, or when you raise a power to a power, you're really multiplying the exponents. So that's what you're doing with the logarithms. So let's look at an example here. It says use log base 3 of 5 to be about 1.465 to approximate the value of log base 3 of 405. So the first thing I need to do is rewrite log base 3 of 405. And so I'm going to use this in here. So I need to have a log base 3 of 5 here. So if I have log base 3 of 5, that means if I take this 405 and divide by 5, this can be rewritten as 5 times 81. So that would be log base 3 of 5 and then log base 3 of 81. But I want to rewrite 81 with log base 3. So since I have a multiplication, this is going to be plus log base 3. And if I have base of 3, 81 can have 3 raised to the 4th power. And now I can use the other property. Because I have an exponent on the base here, I can put that out in front. And so now I have log base 3 of 5, which was said to be 1.465 plus 4 times log base 3 of 3. Remember, log base 3 of 3, that gives us 1. So already I have 4 times 1, which would be 4. So now I have log base, actually not log base, I have 1.465 plus 4, which would give us an answer of 5.465. And that would be our estimated answer for that problem. Letter B, use log base 7 of 3 to be about 0.5646 to approximate the value of log base 7 of 147. Now I need to have log base 7 of 3 here. So if I do 147 divided by 3, I get 49. So this one I can write as log base 7 of 3 plus log base 7 of 49. Log base 7 of 3 we have right here as 0.5646, and we're going to add. Here I can do it as, this is log base 7 of 7 squared. If I put the 2 in front, I'm now going to have 2 log base 7 of 7. Log base 7 of 7 is 1. And then 2 times 1 is 2. I add the 0.5646 and I get an answer of 2.5646. Next, example 3 says use log base 8 of 5 to be about 0.7740 to approximate the value of log base 8 of 320. Now I need a log base 8 of 5. So I can write this as, I'll put that over here, log base 8 of 5 plus, if I did 320 divided by 5, I get 64. So it would be log base 8 of 64. And 64 can be rewritten as 8 squared. And now I can put this 2 out in front, and now I can write the estimated parts. So log base 8 of 5 is 0.7740 plus 2 times log base 8 of 8 is 1. So this will give us an answer of 2.7740. Next, use log base 3 of 5 equaling 1.465 to approximate the value of log base 3 of 9/5. Now for this one, if I separate this as a division problem, or as a subtraction problem, I would have log base 3 of 9 minus log base 3 of 5. Now log base 3 of 9 can be rewritten as 3 squared, which I can write this as 2, and then log base 3 of 3 is 1, minus log base 3 of 5 is written as 1.465. So 2 minus 1.465 gives us an answer of 0.535. And letter B, use log base 7 of 3 to approximate to be about 0.5646 to approximate the value of log base 7 of 98/6. So I would have log base 7 of 98 minus log base 7 of 6. Now actually, before we do anything, let me erase this part right now. Let's simplify this fraction first. I can divide this by 2 halves, and I would get 49/3. Now let's do the log base 7 of 49 and log base 7 of 3. Now I can rewrite log base 7 of 49 as log base 7 of 7 squared. This undoes each other, and that leaves me with 2 minus, and log base 7 of 3 is 0.5646. This is going to give us, so 2 minus 0.5646, we have 1.4354. Now in all of these, I know you could put these into your calculator to solve it, but to show that you understand the properties and they want you to use the estimated or approximate values, you do need to show your steps on how to solve those. Next, solve this one, log base 6 of 5 to about 0.8982 to approximate the value of log base 6 of 5 divided by 1,296. So if I separate those, this would be log base 6 of 5 minus log base 6 of 1,296. Now we already know log base 6 of 5 is 0.8982. And log base 6, this would be 6 to the 4th power. And I know log base 6 of 6 undoes each other. So that makes it 1, so it brings down the 4. So now I have 0.8982 minus 4, and we get an answer of negative 3.1018. Next, use the logarithm base 2 of 6 to be about 2.585 to approximate the value of log base 2 of 1,296. So I can simplify this one. So this is a power property. So this would be log base 2 of 6 to the 4th power. We just did that one. Bring this to the front, and now we have 4 times log base 2 of 6. Said it was 2.585. So 4 times 2.585 gives us 10.34. Next, evaluate log base 18 of 729. So we have log base 18 of 3, and then 729, that would be 3 to the 3 to the 6th power. Bring the 6 to the front, and we would have 6 times 0.3801. So 6 times 0.3801, and we would get a value of 2.2806. And the next one, need to estimate here. So 243 is 3 to the 5th power. So I would have log base 2 of 3 to the 5th power. Bring this in front, and we would have 5 times 1.5850, which will give us 1.5850 times 5. We get 7.925. In example 6, the loudness of a sound L in decibels is defined by L equals 10 times the log base 10 of R, where R is the relative intensity of the sound. A choir director wants to determine how many members could sing while maintaining a safe level of sound, about 80 decibels. If one person has a relative intensity of 10 to the 6th when singing, then how many people could sing with the same relative intensity to achieve a loudness of 80 decibels? So the loudness is our L. So if we put 80 in for L, then we have 10 log base 10 of R, and R is a relative intensity. And if one person has a relative intensity of 10 to the 6th, I would have a log base 10 of 10 to the 6th here. And that's for one person. We don't know how many people, so we're going to do 10 x times 10 to the 6th in here. Now we just need to solve for x. So to do that, let's first get this 10 to the other side by dividing by 10. That leaves us with 8 equaling log base 10 of x times 10 to the 6th. From here, to undo a logarithm, you have to exponentiate that, so base 10. So now this will give us 10 to the 8th power equals log base 10 of 10. They undo each other. I'm left with x times 10 to the 6th. To get x by itself, I divide by 10 to the 6th on both sides. That will leave us with, when we divide like bases, we subtract the exponents. So this would be 10 to the 2nd power, and 10 to the 2nd power would equal 100. So that would be 100 choir members. And our last one, the acidity of a substance can be measured using the pH scale, which is actually a measurement of concentration of hydrogen ion H plus in moles. Formula is pH equaling log base 10 of 1 over H plus. How much hydrogen is in a liter of acid rain with pH of 5.2? Write your answer in scientific notation. So to solve this one, we put 5.2 in for pH. This is going to equal log base 10 of 1 over H plus. To undo a logarithm, we exponentiate that. So that means that 10 and log base 10 undo each other. Whenever I do it to one side, I have to do it to the other. So right now I have 10 to the 5.2 equals 1 over H positive. I need to solve for H positive, so I need that to be on the numerator, so multiply that by H positive on both sides. Now I have H positive times 10 to the 5.2 power equals 1. Get H positive by itself, I divide by 10 to the 5.2 power. And H positive would equal, and in scientific notation, here's where we're going to use our calculator. So I'm going to go to 1 divided by 10 raised to the 5.2 power. This is actually in scientific notation here. So we're just going to put our answer as 6.3 times 10 to the -6. That e to the -6 power just means I had to move the decimal place 6 places to the left. So it's a really, really small number. So we would have 6.3 times 10 to the -6 as the number of hydrogen we have in a liter of acid rain. So that's our lesson on properties of water.